Hello, welcome everybody, and thank you for joining our Machine Learning in Healthcare Summit. It's one of the few healthcare summits that we've run in the past couple of years, and we're glad to have you join. And I'm really appreciative for everybody for joining here. I know that it's a nice day out, depending on where you're located. Can you guys hear me okay? I just want to make sure that we're okay. If you can, please type in the chat on the right and let me know that I'm coming in okay for everybody. Okay, awesome. Thank you so much. Got a message here. We can hear. Great. So I'll get started here. I just wanted to quickly give an intro for those who I've not had the chance to meet. My name is Dave, and I help out with the Toronto Machine Learning Society and these events that we host throughout the year. We would typically acknowledge the land that we're on, which is in Toronto, but today I'm actually located in Northern Ontario. So for those who are joining us for the first time, you may not be aware that we do a lot of, we start basically with a land acknowledgement. And we believe it's important to celebrate the heritage, the diverse cultures, and the achievements of the First Nations, the Inuit, and the Métis people. So where I'm actually located is in Sault Ste. Marie at the moment, and it's located in Robinson Huron Treaty Territory. So the land on which this community is located on is also the traditional territory of the Anishinaabe. So as part of the proceedings from today, we will be donating towards a fund for the Residential School Survivor Society. So if anybody's interested, we'll send a link there in the follow-up email that we send out. So thank you all for joining again. Welcome. I think you're going to be pleasantly surprised with the talks and the speakers that we have today. We've been running these meetups for a pretty diverse group of people, and we have the goal from day one of bringing together a community that is on the whole spectrum of the chain of those working within machine learning and AI. So they could be on the business side, they could be on the research side, even on the engineering and strategy side. We focused on ML ops more recently in the past year, but we do like to do these industry-specific events and make sure that the community is mobilized, that we have a lot of people from diverse backgrounds, and giving the chance for those to meet some people that you wouldn't have a chance to meet with otherwise. So typically we'd be meeting in person. It's usually fun. We have some food, some drinks. Unfortunately, we can't do that, but hopefully towards the end of the year, maybe next year, we'll be back in person again. Now, we want to offer content that's practical, not just sponsored content, make it accessible as possible to the lowest barriers of entry. And one, as I mentioned, that brings together all the academics, the folks from the business and strategy side, technical and non-technical members of the community. So you'll see today a lot of the talks are more research-based, technical-based. We do have one or two that's not so technical. So hopefully you branch outside your comfort zone a little bit and learn something that you wouldn't have had a chance to otherwise. We look for a lot of feedback and ideas from the community. This is a community-based event, so we hope you could provide the feedback, and we'll be sending a feedback form afterwards so you could let us know how you found the event. Just a couple housekeeping items before I introduce some of the folks who will be joining today. One, Chrome browser is probably the best way to avoid any bugs. If you're on a company VPN as well, you might experience some issues. So we recommend the Chrome browser where possible, not on your phone, not on a tablet so much as a desktop or laptop as well. Second, you're encouraged to ask the speakers questions. This is something that we've learned as we transition to virtual, is that one of the benefits is that the speakers are always very generous and they will dedicate their time to answer all the questions. In a lot of cases, they'll provide their email, their LinkedIn, ways to contact them. So if you think of something afterwards, you have them in your network, you could contact them, you could ask questions. And I was really impressed with some of the workshops yesterday because those speakers were really generous. And I think a lot of folks that attended the workshops made some interesting connections there, which makes us happy. So this is how you'll get the most out of this interactive component of the event. You can message people openly, you can message people privately. You'll see on the right-hand side, you could toggle between the event, which is the general sort of event stage, but also the sessions tab. So when you go into the sessions, which will be on the left-hand side, you'll have a separate session chat. You can always go in and see the people who are present at the event. You can message them, and you can request a personal video chat with them, or just send them a message, say hi. So yeah, that's very interesting. The questions, I think the value from this event, and the way in which you're going to get a lot of value is, one, put yourself out there a little bit, get outside your comfort zone, ask some questions. Nobody's going to be judging you. Nobody's, I think imposter syndrome runs rampant in the AI and ML space. And I've seen that from the highest to the beginners because it's so new, right? It's so new. So be willing to put yourself out there, ask a question. We're not here to judge. We're an open group that accepts all questions. And you know what? A lot of these sessions will be recorded and shared. So for those who are watching afterwards, some of those questions might help them. We don't put your name, we won't put who's asking the questions. It'll just be a question, and others will most definitely benefit from that. Lastly, if you're hiring, job seeking, or just networking, you could go to update your profile and mention that in your profile, right? That makes it easier for people to contact you if they're maybe looking to hire or so on. So cool. I think that's good for that. The sessions tab will update. So 5 minutes before every talk, when you click that sessions button on the left-hand side, you're going to see the sessions start to pre-populate. We don't put all of them there just because it'll be a little overwhelming, but those will be the most updated set of talks that will be coming within the next couple minutes. I want to start by thanking all of the volunteers, our committee, the steering committee, who I'm going to introduce, who've helped out and have been very friendly. The staff on our team, the speakers as well, obviously, for making this happen, for providing their knowledge and sharing it and taking the time, and also for you for joining. There's always a couple blips because it's online, it's virtual, it gets a little confusing, but thank you for your patience. I'm very grateful for your participation, as is our team. It's been a weird year. It's been odd. I know that we've been a little disconnected. So for us to be able to meet in person and still be able to pull those off, it means a lot. It really means a lot. Thank you for the sponsors who have joined. They are also sponsors that I believe in. I think they're great, and I think they offer a lot to the community. So first of all, Alta ML. They, in the absence of Element AI, they sort of acted as a bridge between cutting edge academic research and commercialization and industry. They have backgrounds in both, and they've been doing some really interesting things. They have a $100 gift card that they're giving, and you'd be surprised. A lot of people don't take the time to go into the booth sessions. Just click one button and you're eligible to win a $100 Amazon gift card. So I encourage you to do that. Tenstorrent as well. They are really evolving traditional chip design specifically for machine learning. And they have Jim Kelly as their CTO. He's a famous Silicon Valley chip inventor. I think he created the iPhone 3 chip. And he's really doing some interesting things. So they have some architecture that enables scalable deep learning, computational resourceful chip design specifically for deep learning. It's really interesting, and I hope you have a chance to click and check that out. And if you go in, you'll be able to keep in touch. And I know they're reaching out to a lot of people as they're looking for industry and academic connections and collaborations. They are valued at, I think, $130 million, but it's interesting because they're just at the starting stages. So they're really interested in speaking with people and getting feedback. The Vector Institute. Vector Institute is a pillar in the community, a group, an institution that I've really looked up towards. And I think they play an instrumental part in the AI community. So they've been huge, a big inspiration. They work with institutions, with industry, with startups, with incubators, with accelerators, and they're really doing a lot to advance AI research and drive its application and adoption and commercialization within Canada. So they're an independent, not-for-profit corporation dedicated to research in the field of artificial intelligence, and they've really been doing a lot. I hope you have a chance to check out their booth, and obviously go and speak with the folks from Vector. They're great. Microsoft Cloud for Healthcare includes data models, cross-cloud connectors, workflows, APIs, and built-in healthcare-specific components. They have an ebook where you could break down AI in healthcare, and they have some really interesting information. Azure Open Data Sets, if you go on to their booth, you can click and get those. And as well, they have a button where you can click as they're giving away free certifications, right? So they have a certification program. You get those without having to pay any additional money. They're giving those away. So I hope you have a chance to go on to their booth. And again, all of these things are a quick click away. You don't have to speak. You don't have to present. You don't have to sign up. It's just you clicking, and then we'll pass on that information so that you're registered and you have their point of contact. Cool. Algorithmia is an MLOps software that manages all stages of the ML lifecycle with existing operational processes. They put models into production quickly, securely, and cost effectively, and they have some interesting links at their virtual booth. They're also giving away a $100 gift card. So again, make sure to go in and sign up. And Loblaws Digital. I think most people joining today are from Canada. If you're not, Loblaws Digital, and Loblaws is one of the largest grocery chains in Canada, and as well, they have the largest repository of first-party data in Canada. So they're working on some really incredible problems. They have some really interesting and impressive talent on their team, and they're also hiring. So if you're interested, make sure to check them out. You could sign up and speak with some folks. And actually, I can put you in touch directly if you're interested. So just send me a message as well. And lastly, Canadian Health Infoway, and they're doing great work. Why is it great work? Because if you're familiar with the Canadian healthcare system, They are working towards a more connected and collaborative system, working with governments, healthcare organizations, clinicians, and patients to make it more digital. So make sure everybody has access to their personal health information. They can book appointments, get prescriptions, view lab test results, and access other health services. So if you're familiar, it can be excruciatingly fragmented, and they're doing some really interesting work to connect that. So I hope you click on and support. So having said all that, I also want to introduce at this point, and I promise I'll stop talking shortly and we'll kick things off, but I wanted to introduce the co-chairs for this event. They put the program together, they modeled it, they were a great help, and I'm really grateful. So I'm going to welcome at this point Azra and Manal. So Azra is the Director of Health AI Implementation, and Manal is the Director of Strategic Health Partnerships, both at the Vector Institute. So with that being said, I'm going to welcome them in and pass the stage over to them.
Hi, can you hear me?
We can.
Perfect. Hello, bonjour. My name is Manal Siddiqui, and I'm the Director of Strategic Health Partnerships at the Vector Institute. I'm joined here by my colleague Azra, and I'll let her introduce herself when she speaks. I would like to begin by acknowledging the land that Vector stands on, which is in Toronto. Which is the traditional territories of many nations, the Mississaugas of the New Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, the Wendat peoples. This land is now a meeting place for many nations, Métis and Inuit people, as well as newcomers to Canada, like myself, from around the globe. We acknowledge that Toronto is covered by Treaty 13, signed with the Mississaugas of the New Credit, and the Williams Treaty, signed with multiple Mississaugas and the Chippewa bands. And we're grateful to be hosted on this land. I just want to say that it's not that we do this pro forma Lang acknowledgement and that's it. I am proud to be part of the Vector Institute that is taking some serious steps to really engage with the various peoples of this land, as well as newcomers, not just in our programming, but as well as within the AI field writ large. So stay tuned and connect with us if you want to learn a little bit more about what we're doing within the equity and diversity space as well. That said, we are here today for the Toronto Machine Learning Health Summit. I can never get the wording stage right, but so I would like to thank TMLS for hosting us, and for David, Faraz, and Tina for just helping out, and Kiara on our end for helping to arrange this. I would like to thank everybody who applied to speak, and we're just sorry we couldn't accommodate everyone, but we do look forward to hearing from you at future events. At Vector, we believe that Canadians have an unprecedented opportunity to harness world-leading AI research, to build on the data advantage stemming from our public health system. And the Vector Institute supports and enables its partners in health and academic sectors to implement leading AI research to support better whole life health. With that said, I'm just we're gonna really quickly take you through our quick slide deck that's also available in our booth, and I do encourage you to check it out. If I can just figure out how to share. Oh, my apologies. All right, let me know. We're good? We're good. Okay, perfect. So, the Vector Institute was established in 2017 as an independent not-for-profit organization and excels in the areas of machine learning and deep learning. We are a community of over 500 active researchers with expertise in both the theoretical sides of AI as well as applied. We have various pillars within the organization, and health is unique in that there is a dedicated team for this applied area for machine learning research. And just quickly, we partner with health institutions to help deploy machine learning solutions to some pretty complex problems within the system. So we work with different research groups as well as implementation groups to help roll out projects. So we're in the process, and Azra will speak a little bit more into that. We're also in the process of developing governance frameworks that will ensure that AI within the healthcare system is protects our is safe, reliable, and protects our privacy, which is at the center of how we're responsibly deploying AI. And finally, AI wouldn't be anything without data. This is just a quick synopsis to give you just a quick snapshot of like just where data comes from. And so, we're interacting with the healthcare system in so many different ways, and all these are leading to treasure troves of data, which is beyond human capabilities to compute. So I'm really excited to hear from all our speakers today, and I will pass this over to Azra.
Wonderful. Thank you so much, Manal. As Manal mentioned, my name is Azra Dalla, and I also represent the health team at the Vector Institute. And just to quickly build on the information that Manal just shared, I thought I would take a few minutes to just share some of the exciting work that our organization is engaged with, and some of the focus of areas of research for our health researchers. Our researchers are exploring ways in which we can use AI and machine learning to transform how healthcare is delivered, both within the clinical environment and also empowering users outside as well. And some of the information actually will be presented to you by our researchers today. But just to name a few areas of focus, they include medical imaging, cancer research, genomics, neuroscience, and operations. And as you can see on the screen, there are a number of other areas of opportunity. And if you visit our booth, you'll be able to see them fully. Next slide, please. At Vector, we also partner with healthcare institutions to apply machine learning to health data in order to realize the potential of AI to improve patient care, to reduce health service delivery costs, and also to uncover new valuable health-related insights. And a few projects that I've highlighted on this screen today include a series of early AI deployment projects supported by Vector and led by hospitals, university, and institutions. And working together, our goal is really to create the conditions that are required to lead the translation of AI research to healthcare. So for example, Unity Health at St. Michael's Hospital has deployed a system that uses inpatient data to be able to predict when a patient would need a transfer from the general internal medicine unit to the ICU, thus enabling earlier interventions. UHN, the University Health Network, is testing a mobile app that can remotely monitor vital signs and symptoms for patients with congenital heart failure, and it sends an alert to health practitioners who are in the patient's circle of care as soon as these signs or symptoms actually go beyond a predicted boundary. Next slide, please. Our researchers, their methodologies, and the questions that they're exploring have been published in many reputable journals, international journals, which really brings together or actually expands the AI and machine learning health agenda on a global level. And this is all while contributing to thought leadership around Ontario and Canada's role in AI as well. Next slide, please. And finally, organizations and service providers within the health sector can engage with Vector in a number of different ways, and we've listed them on the screen, but this information will also be available at our booth. But just to quickly run through them, the first being industry sponsorship, and this is to support your company's innovation agenda to be able to contribute to technical agility, workforce development, If your company is already a sponsor, there's a number of events for you to attend and opportunities for you to engage. So please do check out our events page for that information. Another way to get engaged is via AI Research Talent Co-Recruitment, which really supports AI talent recruitment at your organization, thus helping to build capacity. And finally, establishing data partnerships. And this is really to further enable machine learning research. As Manal mentioned, being able to utilize the data, to harness the data in partnerships is really going to be able to help move our agenda forward in health AI. So visit our website, visit us on our booth. If you are interested in connecting, you can connect directly with our health team at health@vector.ai. And with that, I'll pass it back to Dave. But before doing that, wanted to thank our audience so much for joining us today. And we look forward to future engagement with you all.
Azra, thank you so much. And Manal, thank you so much for co-chairing, for helping out, for the support of Vector. We really appreciate it. Okay, so what we'll do now is we're going to move on to our first speaker of the afternoon. So this first talk is going to be on open source privacy preserving inference in medical imaging. And Dr. Divya Gupta is a senior researcher at Microsoft Research in India. Her research interest is cryptography and its application to security and privacy. Currently, her work at MSR focuses on secure multi-party computation and blockchains, and in particular, making cryptography practical, usable, and performant. She has published several papers in top computer science conferences such as Crypto, Eurocrypt, IEEE, S&P, ACM, CCS, OSDI, and so on, and holds 3 US patents. She was a postdoc at UC Berkeley, has a PhD at the University of California, Los Angeles with Amit Sahai. Her PhD dissertation was recognized by the Dissertation Fellowship and the Demetrius and Chorafas Dissertation Award, given for outstanding work in engineering sciences, medicine, and natural sciences. And alongside Dr. Gupta is Raul Reina, who is the senior data scientist specializing in AI and computer vision and blockchain at Microsoft Canada's Customer Success Unit. So as I welcome them onto stage, I will let them present the first talk of the day. Thank you again so much for joining, and I will pass it over to you both.
Hi, everyone. Hi, David. Can you hear me?
We can, yes. Thank you for joining.
Thank you.
Hi, David. I think I can start by sharing my screen.
Yeah, that would be great, Divya. Thank you.
Yeah, just 1 second. You're able to see my slides, right?
Yes, I can.
Yes, we can.
Okay, so first of all, thanks everyone for inviting us for this talk. I'm very grateful that Divya is going to be talking about her cutting edge research. I'm just going to set the stage for this presentation, and most of the talk will be given by Divya. So Divya, could you please go to the next slide? And so about a year ago, when the pandemic hit, we were in a situation where there was no clear idea about the symptoms of COVID. Like in February, March timeframe, people were still struggling. How do we identify if somebody actually has COVID versus pneumonia or a flu? And several researchers around the world, they took the approach of using X-ray image-based detection classification in order to detect COVID, including researchers from University of Waterloo, especially COVIDNet. But really at that time, there were only 300 X-ray images available publicly. And as many people tried to build their own models, we obviously tried that approach too. And with our services such as Custom Vision and Azure Machine Learning, we were able to build models within 5 minutes with a high degree of accuracy. But that raised a bigger question. That it's not just about building models, it's about how do you do it in a secure way? Because the way our healthcare system operates in Canada is that we've got a hospital which has an intake unit for emergency patients who are coming in, and then they need to be diagnosed. They have an X-ray capability, but at the time when there's a peak wave going on, they're completely overwhelmed. And in general, when we started seeing the number of case counts of like thousands of patients per day, it became obviously natural that if we were to go down that approach, we would have to rely on other independent clinics that provide X-rays in order to provide the diagnosis. However, the key thing was, how do we protect the privacy of the individual? Because a lot of the data sets that were being shared online, they had this patient information. And there were many researchers who obviously did take approaches to anonymize the data and feed their models. But we thought, how do we do it more securely? And that's where we thought of using secure multi-party computation. So the idea was that, how do we jointly compute a function in such a way that the model is able to infer or predict that a person has COVID or not? And it could be technically applied to any sort of medical condition, whether it's AIDS or cancer or whatever medical diagnosis there is. How do we infer that But at the same time, the patient is in control. They will find out the result. And then it's up to them. They can take the next steps of, maybe not share that information or share that information. But ultimately, you are giving back control to the patients while securing the entire process. And that's where I worked with Divya Gupta and others in Microsoft Research in India and Microsoft Research US to basically come up with a proof of concept to see how we can use some of the open source projects like EasyPC that they have built with cryptflow to build such a solution. So without further ado, I would like to share the stage with Divya so she can elaborate on her research and give you more insights about how we built such a amazing private AI solution. Over to you, Divya.
Thanks, Rahul, for the wonderful setup of the problem of secure diagnosis. Another scenario which we've been hearing repeatedly from hospitals like Stanford Hospital is that they continuously get bombarded by the startups in the Silicon Valley who claim to have the latest and the greatest machine learning model to be deployed in healthcare. So on one hand, the number of models being developed for healthcare are continuously increasing. On the other hand, there are these concerns about generalizability and bias in these algorithms which are coming to forefront. So in this situation, it is critical for hospitals to do a pre-deployment evaluation of these models to ensure that their performance is in line with the expectations of the end users or the patients. For this, the hospitals typically have their own patient data, which is not public, which they want to use to test which model performs best on their data. So the goal is that the hospital wants to determine, like among all the models available, which of the models work best for their patient's data. And this has to be done while preserving the data privacy requirements. So for example, the patient data cannot be made public or given to the machine learning vendors for two reasons. One, legal and regulatory reasons. And two, this test data is small and you don't want the machine learning models to be overfitted to the test data. And hence this cannot be given to the machine learning vendors. And on the other hand, these models are intellectual property of the machine learning vendors and they want to monetize it. And hence they cannot give the model as is to the hospital before some contracts are signed. So the question is, how do you do model testing in this environment of low trust or data silos? So both these problems, the one described by Rahul of secure diagnosis, as well as the secure model testing, are special instances of what is known as secure machine learning inference, in which you have two parties. One is a model owner who owns the model, and the other is a hospital or patient or someone else who owns the patient data. And these two parties do not want to share the sensitive information with each other. And the question is, can these two parties perform machine learning inference collaboratively without revealing the model or the input to each other? So what we are asking is, can we compute a function without revealing both the inputs to any single party? This seems impossible at first. How can you compute the function without knowing the inputs? But surprise, surprise, cryptography makes this possible to get this strong security guarantee that you can hide the inputs and compute the function. So there's a tool called secure multi-party computation in cryptography, which has been very well studied, which enables this scenario. So what is secure multi-party computation? In this scenario, in general, there are multiple parties, any number of parties. Here I've shown 3 parties, P1, P2, and P3. Each of these parties have their secret data, say x1, x2, and x3, and they want to compute a public function f on their inputs. So what MPC gives you is an interactive protocol in which these 3 parties will talk to each other back and forth in multiple rounds of messages, and at the end, the parties will learn the function output. It comes with a strong security guarantee that parties only learn the function output, that was the goal, and nothing else about each other's sensitive information. Moreover, any arbitrary function can be securely computed with this security guarantee. That is, MPC is complete and any function that you can think of can be computed securely. So let me try to explain this scenario of MPC with a very simple and classical example of millionaires problem. So here consider that there are 2 millionaires, Alice and Bob, and they each have their net asset value. They want to learn who is richer, whether it is Alice or Bob. That is, they want to compute this function f, which just compares the net worth of both the parties. And as you can imagine, the net worth of the parties is a sensitive information, so they want to compute this function without revealing their net worth to each other. This is exactly the scenario of multi-party computation, where there are multiple parties, here there are Alice and Bob, who want to compute a function where each party has a sensitive input to that function, which is their net worths, with the added condition that inputs should remain private, modulo the output which they want to learn. So let me spend a slide trying to explain what does it mean to compute a function where you learn the output and nothing else about the inputs. So here in the simple scenario, you have Alice and Bob with the secret inputs x and y. They want to compute a function f. So let me show you a dummy protocol, very conceptual one, which lets you achieve this. So say Bob will pick an encryption key k and just encrypts his input y and send to Alice. What Alice will do is she'll do a lot of hard work on the ciphertext and come up with something which is an encryption under the same key k of the function output f computed on x and y and sends back the ciphertext to Bob. Now, as you can see, since Bob picked the key and did not give the key to Alice, by just security of encryption, it is clear that Alice learns nothing about Bob's input. Moreover, it can be shown that since Bob only sees the ciphertext which encrypts the output and nothing else about Alice's input x, Bob only learns the function output and nothing else about Alice's input x. So MPC gives the same guarantee, but instead of the simple conceptual protocol, you have a much more involved protocol in which Alice and Bob talk back and forth in more than 2 messages, depending on the function complexity. And we can formally prove that these messages give no information about Bob's input to Alice. Put intuitively, you can think that suppose Bob has 2 inputs, y or z. Now, from Alice's view, she cannot tell in the interaction whether Bob used input y or input z. Similarly, one can also qualify the security arguments against Bob, where one would show that Bob only learns the output. For this, we show that all the messages which Bob receives from Alice are completely simulatable given only the output and nothing about Alice's actual input. Okay, so coming back to secure inference. As I said, secure inference is a special case of general multi-party computation where we have 2 parties, the model owner and the data owner. They want to compute the inference without exchanging the model and the input with each other. But the problem is that general MPC protocols, when applied to secure inference, are very inefficient. And since the secure inference problem is very important and has lots of applications in healthcare and even otherwise, this problem gained a lot of popularity. And a lot of work has went into designing specialized protocols for this problem of secure inference, but they all fall short on 3 aspects, which are efficiency, scalability, and programmability and usability. By efficiency, I mean the end-to-end latency of secure inference protocol. So while it is clear that secure inference protocol is going to be slower or will take more compute and communication compared to just running it on claytext, the current state of the art was quite bad, and this is an active area of research to improve the efficiency of secure inference protocols. Next is scalability. As we all know that machine learning algorithms are becoming bigger and more complex, and we want to be able to run the latest and the greatest of machine learning models using secure inference protocols. But the prior state of the art was only evaluated on small machine learning models on tiny data sets like MNIST and CIFAR, and are far from scaling to real-world models, especially deployed in healthcare. And the final challenge is programmability and usability of these secure inference protocols. I, as a cryptographer, can vouch for the fact that these secure inference protocols, or MPC in general, is quite complex and subtle. And it's completely unreasonable to expect developers who have no prior background or formal training in crypto to be able to implement these protocols efficiently and securely, and that too for large machine learning models. So with these 3 challenges in mind, Here's our goal put simply. We want the developer to only write what needs to be computed securely and not how to do it. And then at the push of a button, we want the crypto and compiler magic to happen, which outputs secure and efficient implementation based on MPC protocols. We want our compiler to be error-proof, that is, insecure implementations should not type check. And user-centric, that is, the developer only writes the vanilla code which describes a function to be computed, and our compiler does all the cryptography. For a compiler to work efficiently, we want the compiler to be crypto cost aware. That is, given the building blocks of crypto, the compiler has to put them together in an intelligent way so that the resulting protocols are secure as well as efficient. With these goals in mind, the work at MSR can be summarized as designing better cryptographic protocols for secure inference that work well on large machine learning tasks, as well as better compilers that provide this push-button solution, and both of these should scale to real-world machine learning models. The outline of the rest of my talk is as follows. First, I'll just give a very brief overview of our results for new cryptographic protocols. Then I'll describe our system from the user's perspective. And finally, I will discuss the various case studies from healthcare. So before getting into how does a secure inference protocol work, let's just look at what does a machine learning model look like. So here I have an Onyx graph of ShuffleNet model. And as you can see, some of the nodes are matrix multiplications and convolutions, which are commonly referred to as linear layers. Then we also have ReLU and MaxPool and also average pool, which correspond to simple activation functions used in neural networks. And more complex machine learning models also use mathematical functions like sigmoid, tanh, and square root. So our task is to design specialized protocols for each of these nodes and combine them securely to get a protocol for inference of the end-to-end model. So just to take a closer look at these functions, for doing matrix multiplications and convolutions, one needs to do additions and multiplications, whose protocols are well known for quite some time. But for simple activations like ReLU and MaxPool, you need to do comparisons, and average pool requires a division. And these protocols were not efficient in the prior state of the art, and in fact, they were the major bottlenecks for scalability. So in our work, RIFFLOW 2, published at ACM/CCS last year, we studied and gave specialized protocols for these functions. And finally, math functions are the most complex and involved, and was the focus of our work Siren, which is published at IEEE Security and Privacy just this year, where at the first step, we gave numerically precise and crypto-friendly representations of these math functions. And then we gave efficient custom 2PC protocols for the same. So just to give a high-level overview of how the cost of different gates vary, addition is completely free of cost, takes nothing. Multiplication is slightly more expensive, and the two parties need to communicate with each other. Comparisons and division are much more expensive and require higher communication. And finally, math functions are most complex and most expensive in terms of compute as well as communication. But it is well known that the major bottleneck of performance for scaling to large machine learning models is the amount of communication. That is the total size of the messages which need to be exchanged between the two parties in the protocol. And in our work, RIFFLOW 2 and Siren and others, we give specialized protocols for all of these activation functions, simple as well as math functions, which require much less communication compared to prior works, and hence are much more performant than them overall. So here's a glimpse of a result from RIFFLOW 2 to show how much we improve the prior state of the art. So here I'm looking at 32-bit integer operations and three commonly used operations, which are comparisons, which are used in ReLU as well as MaxPool, and also internally in our math functions. Then we consider ReLU and average pool. So for comparison or millionaires, which I described before, it's a very well-studied problem since the beginning of MPC. And here we reduce the communication by more than 4 times. Since comparison is used in even other protocols, this is beneficial for all our protocols. For ReLU, we reduce the communication by almost 10 times. And for average pool for a 7x7 filter, we reduce the communication by over 50 times, and this uses our specialized protocol for division. Now I will move on to describing our CryptFlow system. So to address the challenges of programmability and usability of secure inference protocols, we have built a system CryptFlow, which starts with a native TensorFlow or ONNX inference code, and at a push of a button does crypto and compiler magic and outputs efficient MPC protocols. Unlike other systems out there, the output code of a compiler matches the prediction accuracy of TensorFlow, and there is no loss in accuracy. Since the developer only writes native TensorFlow and ONNX code and doesn't need to do any additional work or no crypto, our system is programmable. And we have shown that a system scales to large models such as ResNet 50, DenseNet 121 on ImageNet, and even larger real-world models for healthcare, which I will talk about. So here's a high-level workflow of our CryptFlow system. So first we take the TensorFlow ONNX code and do the metadata generation, which computes the sizes of the tensors and does the float-to-fixed conversion and compiles it to EasyPC, which is a C-like intermediate language. It is perfectly okay for a programmer to even write in EasyPC instead of TensorFlow. Even here, the programmer can be completely agnostic to crypto and only needs to write what needs to be computed in a C-like language. This makes most sense when you're doing some non-TensorFlow-like applications such as decision trees, random forest, or even some non-machine learning application. Then we compile EasyPC to an MPC protocol, and here we have options of multiple protocols, 2-party, 3-party, and others. And finally, at runtime, parties feed in their private inputs to learn the output. As I said, our system is developer-centric. So let's see how does a developer use our system. So in the problem of secure inference, we have the two parties. One is the model owner and one is the data owner. So at the first step, model owner will split the model into two parts. The model structure or the skeleton of the model, which is the public function which we want to compute, and the weights of the model, which is the secret sauce which went into building the model. It will feed in the model structure or the TensorFlow ONNX code to the CryptFlow system. And out comes two binaries to be run by the two parties, model owner and data owner. Next, at runtime, the model owner will feed in the secret weights, hospital will feed in the patient data. The two binaries will interact with each other in multiple rounds of messages and finally get the function output. So our CryptFlow or EasyPC system is not only programmable and usable, but also the absolute state of the art when it comes to performance and scale. So here I've shown a comparison of the largest benchmarks run by various systems out there. I'm using the number of flops in a neural network, which is number of operations, as a proxy of the size of compute. And I'm forced to show in log scale because otherwise the other systems won't be visible. As you can see, with EasyPC or CryptFlow, we are able to run models of size almost 2 teraflops, whereas the prior best, Delphi, was only 150 megaflops. This is the first system to run real-world machine learning applications, and our system suffers no accuracy loss. All this has been possible with crypto and compiler code design. And all of this comes with formal security guarantees that the corrupt party learns nothing but the function output. I will conclude this section by talking about few benchmarks on ImageNet. So ImageNet used to be a competition a few years ago, and the task is quite complex. So here, given an image, you need to classify it into one of 1,000 classes, which look like Eskimo Husky, Alaskan Malamute, Siberian Husky, and so on. And as you can guess, this task is quite complex even for humans. We looked at 3 benchmarks on ImageNet, SqueezeNet, ResNet 50, and DenseNet 121, and did the first ever evaluation at this scale using MPC technology. As I said before, the performance of MPC is bottlenecked by the amount of communication. And hence end-to-end latency is largely dependent on the amount of bandwidth between the two parties. So we ran our experiments both in the LAN setting and the WAN setting. LAN setting had two parties in the same region and hence had much better bandwidth. WAN setting, the two parties were cross-continent, East Europe and East US, and hence the bandwidth was much worse. Nonetheless, all of these benchmarks complete within 10 minutes on the LAN setting and 20 minutes on the WAN setting. Now I will move on to our case studies in healthcare. Let me begin by the first case study, which was, as described by Rahul, COVID-19 diagnosis from chest x-rays. So here, one party, the model owner, has the model which predicts whether the x-ray has COVID or not. And on the other hand, we have Bob, who has a sensitive x-ray image and wants to know the prognosis based on this classifier. So for this task, we trained a ShuffleNet V2 model using publicly available data and ran it through our crypto system. Secure inference for this task took only 72 seconds. So as you all know, chest radiography is one of the most commonly used medical imaging globally and is in fact critical for many life-threatening diseases. And hence, a lot of work has been put in to train models that automate the task of chest radiograph interpretation at the level of an expert radiologist. So here we looked at the Chexpert model from Stanford, which is the absolute state of the art for classifying an X-ray into 14 lung diseases based on their likelihood. We ran this through our liquid flow system, and secure inference for this task takes about 15 minutes. Next, we looked at an RNN for wet AMD. This is a model developed by Novartis and MSR. This is a time sequence model that looks at the data from current and last 2 visits to the doctor and predicts when to visit the clinic next, whether after 1 week, 2 weeks, or 4 weeks. The model has a GRU kernel, which has tanh, inverse square root, and sigmoid math functions. And to run this efficiently, we relied crucially on our new math functionalities from our work Siren. And secure inference for this model only takes 19 seconds, so it's almost real time. Then we challenged ourselves to run secure inference on even bigger models, such as the ones used for secure segmentation in personalized radiotherapy. So here the task is as follows. You're given a 3D scan of a patient, and one needs to mark tumors and organs at risk in this volumetric scan. This is quite a painstaking task and takes a skilled doctor more than a couple of hours to do it manually. So to increase doctors' productivity, Addenbrooke's Hospital from UK and MSR Cambridge got together and trained this machine learning model 3D-UNet to automate this task, which can be followed by a quick verification by a doctor in 20 minutes. This model is very big. It's like 2 teraflops model, way larger than ImageNet models. To quantify, this is 500 times bigger than ResNet 50 on ImageNet. And plain text on this model takes more than 30 seconds on 4 V100 GPUs. This is because of the huge memory requirement. And as you can imagine, 2PC does not scale to this task. ResNet 50 took 10 minutes, and 500 times 10 minutes is a lot of minutes. So to run this model securely, we considered an alternate model in which, along with the 2 original parties, which is the model owner and the data owner, we have a third party, which is the helper party with no inputs and simply aids in the task of secure computation. And security holds as long as at most one party is corrupt and no 2 parties collude with each other. 3-party secure computation in the setting of no collusion is much more efficient than the 2-party secure computation. So we took this Unit 3D model and ran it through Cryptflow system with a 3-party secure computation backend, and the model runs in approximately 2 hours. We are told that this is an acceptable latency because results are not needed before a couple of days. And this 2 hours was just on CPUs, whereas the clear text was on GPUs. This is the first ever secure evaluation at this scale across all privacy-preserving technologies. Finally, I would like to discuss our results on secure model testing, which is a work done in collaboration of MSR, Stanford Center for AI in Medicine and Imaging, and Kering Lab from New Delhi. The scenario is as follows. As I said, Chexpert has the absolute state-of-the-art model for detecting lung diseases. On the other hand, Kering has its own patient data and wants to determine how well does the Chexpert model trained on Stanford data perform on the Kering data set, which is collected in New Delhi. For this, we ran the secure inference on all of test images and computed the AU-ROC score and found that the model works well. As I said, secure inference on one image took 15 minutes. So total time to run this experiment was 15 times 500 minutes on a single VM. Of course, this scenario could have been realized by doing complex legal agreements between Chexpert and Kering, which say that Kering will not steal Chexpert's model, etc., etc. But with our technology, we could do it with 5 days of cloud compute and under $100 of money for the end-to-end experiment. With this, I would like to conclude by saying that current state of privacy-preserving technologies is practical for use in healthcare today. We have built this system CryptFlow, which is open source and can be used for privacy-preserving inference in medical imaging and other scenarios. Today, I showed you 2 case studies, one from many studies from secure inference and one study from secure model testing. We support both 2-party secure computation as well as 3-party secure computation in scenarios where a choice of this third party is natural and no collision assumption is met, and you can get much better performance. We automatically compile from TensorFlow or ONNX inference code to secure computation, and this compilation preserves the prediction accuracy of native code. Our system outperforms prior works in both latency and scale by orders of magnitude. And you can reach out to us at easypeasy@microsoft.com if you have these scenarios, or you can yourself test out our system, which is open sourced on GitHub. With this, I would like to conclude my talk. Thank you.
And thank you so much, Dr. Gupta and Rahul. That was fantastic. And for those, who are interested in learning more about CryptoFlow, or if they have any questions, they check it out on GitHub. Are they able to contact you via LinkedIn or email, or is there a way for those who may have some questions to keep in touch?
Yes, so there's this email ID, easypeasy@microsoft.com, and that's our group ID.
Thank you so much. So we have a couple questions here. I'm not sure if you can see on the stage, toggle on the right-hand side.
Should I stop sharing my screen? And I'm not able to see the...
You know what? I'll ask. I think that's okay, because you might want to go back. So about 12 minutes ago, somebody asked, why bring the data to the model? Wouldn't it be better to bring the model to the data for better efficiency?
You mean in the insecure scenario, right? So, I'm talking about scenarios in which there are 2 parties and both parties have sensitive data. In case it is okay to ship the model to the client, then MPC does not make sense. But in scenarios where model itself is an intellectual property and cannot be sent to the client for prediction, and of course, client's data is sensitive and may not be sent to the model owner for prediction, that's where you should use MPC.
Okay, and Dinesh asks, is only a subset of all TensorFlow ops supported by CryptoFlow? Or is it only a subset, or is it all?
It's not all, but it's a large enough subset for TensorFlow.
Thank you. You mentioned 19 seconds inference time for the retinal image analysis. Is that for a single image?
Yes, single image.
To clarify? Okay.
All the times I showed are for single image inference.
Awesome, thank you. And then Das asks, can this framework be scaled to support model tuning using new layaway data from the hospital?
Yes, definitely. So in our prior work, Secure NN, we also consider training of the models. So you can use that for doing both forward propagation and back propagation using MPC and fine-tune your models with new data.
Okay, thank you. We're going through these questions. quickly, but I appreciate the quick response. It's great. In terms of accuracy preservation, do you have any number? Do you have any number STO report?
Okay. So when I say it matches the accuracy, I mean that you take a model in TensorFlow, and that comes with a reported accuracy, right? Like for ImageNet, it can have some 80-something% accuracy. And when run it through a system, so what happens is that you change the description of the model in some way, that instead of using floating point, you start to use integer arithmetic, because that's more efficient for MPC. And we show that modified model has exactly the same accuracy as the native TensorFlow code, which was not true for other works in this domain.
It's brilliant. Thank you so much. Well, I think that's it for questions. I know that if folks have some questions, they will reach out.
Yes, feel free to at any time, right? This is like, we are super excited with all this work, and we have done numerous case studies from healthcare. So we actually and really feel that this tech is ready for use in healthcare.
Oh, that's fantastic. Well, we'll definitely be sharing this, and we'll share some of the resources that you've provided here. And I really appreciate it, Dr. Gupta, the fact that you're taking the time, not only taking the time, but making yourself available for those in our community that may want to ask questions. And I'm sure that will give them an opportunity to try this out and see if it's going to help them a lot. So thank you very much for pushing this along,
so much
and for sharing.
For having me.
Yeah, we really appreciate that. So awesome. We're that initial keynote's a wrap, and what we'll do is at 1:30, which is I think Eastern Standard Time, depending on where you are, 1:30 my time. It's about 3 minutes away. We're going to be starting on the other sessions. So if you click on the sessions tab, you'll be seeing those populate, and then we'll continue throughout the afternoon. Dr. Gupta, Rahul, thank you so much. I really appreciate you taking the time.
Thank you so much.
Thank you. Bye.
We'll see you folks in there. I hope you enjoy. Bye now.
Bye.